Welcome back to Math 130, Applied Algebra and Trigonometry. Today we're going to be talking about Section 12.5, the exponential form of a complex number. We have already discussed the rectangular form of complex numbers and the polar form of complex numbers, which are related using these equations, which we have discussed. Now let's turn our attention to the exponential form of a complex number. The exponential form is used in electronics, engineering, lots of physics applications, and it's more convenient for multiplication and division of complex numbers, much as the rectangular form is more convenient for addition and subtraction. I'm not going to ask you to get into doing the multiplication and division this semester, but you should become familiar with this exponential form. You will remember from our discussion of natural logarithms that e represents an irrational number, which we will approximate to be 2.71828, and it just keeps going. I will not be discussing the advanced mathematics that we would need to use to explain how we get to this exponential form from the polar form. I will tell you that to do this, we need to work in radians. So rectangular form, we're just going to be working with real and imaginary numbers. In the polar form, we're going to be working with real and imaginary numbers, but we're going to be working with a radius and an angle expressed in degrees. So let me write that here. We're going to be working with degrees. In the exponential form, we are going to be working in radians. So make sure you are in the proper mode if you are ever trying to evaluate a polar form of a complex number or an exponential form of a complex number. Let's make some room to work. So let's take a look at this example, example 1, which is 25.0 at an angle of 127.0 degrees. So that's a complex number expressed in a condensed polar form. What do I have that I can read from this formula? Well, I have that r is equal to 25.0. I have that theta is equal to 127 degrees. All right, but since I want to convert to exponential form, which is what we're working with today, first I have to convert this to exponential form by multiplying by pi over 180 degrees. And now, the moment you've been waiting for, when I allow you to use your calculator to approximate a measurement instead of giving me the answer in terms of irrational numbers or simplified fractions. So if you plug into your calculator 127 times pi divided by 180, you should get 2.217. Or as I like to say, in terms of significant digits, we're looking at 2.22 radians. Now we can rewrite our original complex number that was in the polar form in its exponential form. That's equal to r, which is 25.0 times e to the j times theta, expressed in radians, which we will, of course, rewrite because, as we've talked about before, when you are writing an imaginary number, the coefficient comes first, followed by the j. So although your textbook gives you the formula in this form, I would suggest that you use the equivalent formula, r times e to the theta j, so that you remember to write the j following the coefficient when you get down to this final answer, when you're actually approximating a complex number in exponential form. Let's move some things out of the way a little bit further. And let's move this example over here, make it a little bit smaller, and do another similar example. So let's identify our R as 0.515. Where does that go in the exponential form? Well, it goes right out in front as well. 0.515. And then we have our E, and that is raised to the angle. So let's just emphasize that angle in yellow. However, this angle is expressed in degrees. So before we can just insert our angle, we have to convert it from degrees to radians. And that is approximately 3.46098, and it continues. So we're going to take it, let's see, 3 significant digits, 3.46J. That's our final answer. We have converted from the polar form of a complex number to the exponential form. Now let's throw it into reverse and go the other way. Now, before you jump right in and convert this exponential to polar form, take a little bit of time to think. Do I want to express my answer in degrees or radians? And for that matter, in the form of the complex number that I have, what are the units of the degree? The form is this. So here is our angle. Because I'm using the exponential form, I can be confident for our purposes that this is expressed in radians. So R equals 0.500. But if I want to express this in polar form, I have to convert from radians to degrees. So my complex number can be rewritten as 3.00 at an angle of 28.65 degrees. Now, to get from here to the rectangular format takes a little bit more doing. And there it is in the polar expanded format. And in case you're not seeing it with the color coding, remember that this is where we start when we have polar condensed format and want to get to the polar expanded format. And then this is where we wind up. The expanded format of the same complex number is always R, open parenthesis, cosine of theta plus J sine of theta, and close the parenthesis. From here, we can move on to the rectangular format. To do that, I'm going to rewrite our polar expanded format over here, where I have my rectangular format column. Now I distribute the 3.00 to each of the terms inside the parentheses and get the following. Negative 2.79 minus 1.10J. And all right, here's a quick recap. All of the following expressions of a complex number are equivalent. It is the same complex number expressed in different formats. So we start with 3.00 e to the 5.00j, the exponential form. That is equivalent to 3.00 and then the angle sign with 28.65 degrees. That is equivalent to the original form of the complex number. This is the condensed format for the polar form of a complex number. Then we move on to the expanded format of the polar form of a complex number. And it just keeps going, doesn't it? And then finally, we have the rectangular form of that same complex number. We express it in different ways because it depends upon how we are using it. Which one of these is the better choice and or the easier choice to use. One thing to remember, of course, is always that when you are dealing with the polar form, you are going to be dealing in degrees when you're talking about your angle. Whether it's the condensed polar form or the expanded polar form, when you are working in with the exponential format, you're going to be using radians. Make sure your calculator is properly set up. Choose the correct mode. All right, here's our last example. Let's go from the rectangular form of this complex number, -1 minus 5j, to the polar form. And I have graphed the number here just as a check to make sure we have our angle in the correct quadrant. In fact, let's make this bigger so we can actually work with this and write in the lengths of the sides. Here is our -1 side. Change the color on that. -1. And here's our -5j. So what would the length of our r be, the radius? Well, r would be equal to -1 squared plus -5 squared, but all of that under the radical. We have to take the square root of it. So we would get the square root of 26, which is approximately equal to 5.1. Now I've started to write out the formula for finding our reference angle, but I'm going to change it just a little bit this time, because the side opposite our reference angle will always be our imaginary part. So I'm going to write imaginary in the numerator, and the side adjacent to our reference angle will always be the real part of the complex number. And rather than using my calculator to do the absolute value, I'm just going to drop the negative from in front of the 5 and the negative from in front of the 1. So I'm looking for the inverse tangent of 5. That will give me my reference angle. And after putting my calculator into degree mode, I find that I have a reference angle of 78.69 degrees. As you see from my small diagram there, this is not in the first quadrant. Therefore, I have to add this reference angle to 180 degrees. So let me just do this right here, plus 180 degrees. And that gives us a final angle of 258.69 degrees. So I have found my R value. I have found my standard angle. I'm ready to write out the polar form. If I went through any of that too quickly for you, just stop the video, back up, watch it again. I'm going to skip ahead and put this straight into the polar condensed form. There it is. But let's go ahead and write it in the expanded form as well. And there we see why a condensed form's may be a good idea. Now let's convert degrees to radians so that we can prepare to write this in the exponential form. So there's your radians conversion. And let's write this in exponential format now. The value of r has not changed. It is still 5.1. Then we write e raised to the j, but that j is multiplied by 4.51 radians. This is the same complex number in rectangular form, polar expanded form, polar condensed form, and the exponential form. And that closes out this video. I will see you in class.